All right. Here I'm assuming a is a constant. Let's look at this indefinite integral. So what we got? We've got x squared over, so you know this, when we have a sum in the numerator, algebra says that's the same as x squared over x, right? Plus 4x over x plus a over x. Now if the sum is in the denominator, you're out of luck, all right? If you believe that sort of thing. Anyway, so we have integral of x plus 4 plus a over x, all right? And we can integrate term by term, and what we get, 1/2 x squared plus 4x plus a times the natural log of the absolute value of x plus a constant. Phew, just made it. All right. So sometimes we need to do some algebra before we can integrate, right? All right. So algebra is in fact required. All right. So this I can rewrite as x squared plus 1 minus 1 over x squared plus 1, right? So this is really nothing more than 1 minus 1 over x squared plus 1. And now I'm in business because I know how to integrate 1 and I know how to integrate this fraction, right? So that gives me x minus inverse tangent of x plus a constant. And there you go. So there's another one down. Now, this trick I just did, I added 0, right? Another way to come to that conclusion there, right, would have been to do long division. So here's how that would have gone. Dividing x squared into x squared plus 1. Wait a minute, other way around. Oh, other way around. I'm an idiot. All right, there we go. Sorry. So I put 1, right? Multiplying, fruit fly. Ugh. X squared plus 1. Subtract, you get minus 1. Oh, that's the remainder. And so there it is. That shows you that x squared divided by x squared plus 1 is equal to 1 minus 1 over x squared plus 1. Anytime you have a improper fraction in the sense of a rational function, right? Anytime the degree of the numerator is matching or larger than the degree of the denominator, you can use long division to rewrite it as the sum of a polynomial, in this case 1, and a proper rational function, like so. We will in fact learn how to integrate pretty much any proper rational function that comes at you in calculus 2. Can't integrate there's lots of functions we can't integrate, but rational functions have been, we know how to do those pretty well. All right, tangent squared, well, that's kind of scary, but remember that we have an identity that was tangent squared x plus 1 equal to secant squared x, right? So I can trade tangent squared for secant squared x minus 1, all right? And so, all right, now I'm good to go because these are basic, all right? Integral of secant squared is tangent, because the derivative of tangent is secant squared, and minus x plus a constant. All right. And there you have it. All right. It's important to know about these basic ones because as we learn more techniques, you'll be tempted to try to use a sledgehammer to kill these mosquitoes later, you know? And I don't know if you've ever tried to kill a mosquito with a sledgehammer, but it's not usually a good idea. All right, break stuff. So here we have the integral of d theta over 1 minus theta squared. That is in fact inverse sine of theta plus a constant, because the derivative of inverse sine is 1 over the square root of 1 minus the argument squared. So there's that one. All right. Next on the list, the integral of d beta over beta squared minus 1. Now, I know it's a while ago, but that is going to give us cosh inverse of beta plus a constant. because the derivative of inverse hyperbolic cosine is 1 over the square root of something squared minus 1. All right. Next on the list, gamma. This guy is going to be the inverse hyperbolic sine of gamma plus a constant, remember. The derivative of this is that function, derivative of that is that function, derivative of that is that function. Okay, so admittedly, there are, and I might have to derive the last two in a pinch. I might forget those, but I kind of know, you know, if I see something like this, I know that there is an antiderivative of one of my basic inverse functions. I can go look it up, find it. All right. So there's some more basic examples at this. So, but you know, it's not hard to write down things, right? So what can't we do? You know, what else? What else do we need to be able to do? Well, things we can do will be things like this. X e to the x squared dx, or the integral of cosine cubed theta d theta, or the integral of sine theta cosine theta, you know, or the integral of 1 over 1 plus x cubed to the 14th power, and then upstairs, you know, x squared dx. These things we can do, right? And I'll show you those in the upcoming videos. But you know, eventually there's other things that we won't get to in these videos that are calculus 2, things like this. Integral of e to the x cosine x dx, that we can do in Calc 2, right? With something called integration by parts, or the integral of the square root of 1 minus x squared dx, that we'll learn how to do in Calc 2, but we can't do it with our current technology, all right? This requires trig substitution, this requires integration by parts. More complicated rational functions, stuff like x over x cubed minus 1. In principle, I can do that in Calculus 2 with techniques we learned, partial fractions and so forth. So in these videos, I'm going to cover U substitution and the integral of trig functions, right? In terms of indefinite integration, we still have that to cover. And then I'll talk about definite integrals and a little bit more on the theory. But you know, these things we'll wait for later. Of course, there's another class of functions, you know, which it doesn't matter how much calculus you learn, you can never write the integral in terms of you know, sum or product of elementary functions. And a good example of that is the thing we looked at in the differential calc. Well, I don't know if we looked at it or not. I think my video broke. But this thing, the Gaussian, y equals e to the minus x squared. This is the Gauss, the bell curve, and some of the Gaussian. There is no nice antiderivative for this in terms of elementary functions. But it's of interest, right? So if you take statistics, you'll find tables of integrals tabulated in the back for this guy over specific, well, we'll talk about definite integrals later. But, you know, we can't integrate everything. There's not a way to reverse every. You start a function, you give me a function and say, well, what other function can differentiate to get back that function? There are plenty of functions where you cannot do it, all right? So what we're doing is we're looking through all of the standard examples where you can reverse the differentiation process, where you can do anti-differentiation. But these are precious and unusual things. So anyway, I'll probably, next thing I have to do is initial value problems. So we'll do that, and then we'll do U substitution. Thanks, guys.